In this playlist, I'm showing you how to build a CPU. If you haven't watched the previous video, check out the link to the playlist.
Check it out, check it out, check it out, check it out.
We have covered a lot of ground so far in our journey to understand how to design a CPU. Let's reflect about where we have come from. We started out with a simple electronic circuit and learned some of the basic principles of electronics. We proceeded to understand the role of transistors in digital electronics. Then, we used transistors to build NAND gates, which are the fundamental building blocks of all digital logic. Finally, we used the NAND gates to build all of the foundational Boolean functions. In this video, we will move from our Boolean world into a binary world. We will use the Boolean functions we constructed in the previous video to create binary functions that start to look like recognizable computing constructs. These constructs make up the arithmetic logic unit, or the ALU.
That's amazing.
Let's start by identifying the capabilities of the ALU. The ALU performs a subset of the processor's functionality that deals with math operations and logic. Specifically, the math operations include addition and subtraction. The logical operations include mainly AND, OR, and NOT. We can also add one additional useful operation known as shifting, which moves the position of each bit sideways. We have already looked at the Boolean logical operations of gates. You might be asking, what's the difference between gate-level Boolean operations and ALU Boolean operations? There are two differences. First, we think of gate-level operations as operating on Boolean values, but as we move to the ALU, we think of these operations as working on binary numbers. Really, it's the same circuitry, but we think about it differently. The second difference at the ALU level is that we scale these operations to work in parallel so that we can perform the Boolean operations on many bits, which is an entire binary number at once.
Binary? Binary is just ones and zeros.
Yeah, I know it.
In order to accomplish this parallel scaling, we will introduce some additional control circuitry made from the Boolean gates we established in the previous video. The size of the parallel scaling depends on the word size. A word consists of an ordered set of bits that we use as a standard parameter in the operations of a processor. The number of bits in the set constitutes the word size. Normally, word sizes are powers of 2, for reasons that will become apparent as we work through the design. The choice of the size is somewhat arbitrary. When we make this choice, we want enough bits to represent numbers of a useful size, but increasing the number of bits also adds to the cost of the design. So we want to keep the number of bits small to reduce cost. These counteracting forces cause designers to choose word sizes of 16, 32, or 64 bits. Since we are more interested in exploring design rather than building a world-class processor, we will use a 16-bit word. Before we try to build all the ALU functionality, let's understand how the individual functions of the ALU work. We have already looked at the AND and OR functions at the gate level, which we can directly apply at the bit level. So, let's now take a look at addition. Let's start by creating a circuit for adding two bits together. We call this a 1-bit adder. Yes, we are adding two bits together, but the main output is a single bit, so it's called a 1-bit adder. First, let's look at the truth table for this function. Note that this table is no longer Boolean, instead it's binary. Even though the table is binary, we can treat the values in a way similar to Boolean by considering 0 to be false and 1 to be true. Another interesting aspect of this table is that it has two outputs, one labeled carryout and the other labeled output. These two outputs work together to represent a 2-bit binary number. The output is the low-order bit, and the carryout is the high-order bit. These two bits are necessary when both inputs are 1s, as shown in the last row of the truth table. We will explain later why we refer to the high-order bit as carryout. The easiest way to conceptualize this function is to see each output as its own function. By doing this, we see that the output function is merely an XOR, and the carryout function is just an AND. If you enjoy a challenge,
I enjoy a challenge.
Very well.
pause the video here and see if you can design this circuit using Boolean gates. Here's the schematic for a 1-bit adder. There are two key points about this schematic. First, we moved from Boolean to binary. And second, we isolated each output to simplify the design effort. While adding 2 bits is a step towards computation, it would be much more interesting to understand how to add more than 2 bits. For example, imagine adding two 2-bit values. Here's the truth table for this adder. This is a function with 4 inputs and 3 outputs. Further, the 4 inputs are really 2 sets of 2 inputs each. Each set of 2 has a high-order bit, representing the 2's place, and a low-order bit, representing the 1's place. The 3 output bits represent the 4's place, named carryout, the 2's place, named output 2, and the 1's place, named output 1. Once again, an easy way to approach the schematic design of the entire function is to design the schematic for each individual output, and then combine the schematics. Taking this approach, we see that the 2 low-order bits behave in the same manner as the single 1-bit adder. That is to say, that output 1 for the 2-bit adder is the same as the output for the 1-bit adder. But what about the carryout from the 1-bit adder? The carryout from the low-order bits becomes an input, call it carry in, along with inputs A2 and B2 for output 2. This table shows the dependencies between these 3 inputs and the output. This function is a 3-way XOR, or in other words, an XOR of A2 and B2, where the output is the input to an XOR with the carry in. Finally, we need to look at the third output from the original truth table labeled carryout, which is also a function of the A2 and B2 inputs as well as the carry in. Let's look at its isolated truth table as shown here. This is not an obvious function. We need a different way to think about this strange function.
This is strange.
In the next video, we will discuss how to figure out the design of unusual binary functions using something called Carnot maps. Then we'll be able to complete the design of the 2-bit adder. Subscribe and click the notification bell so you can be notified of this and other future videos.